The French astronomer Janssen reported to the Académie des Sciences in Paris in 1873 his intention to use a photographic revolver to record an important astronomical event, the transit of Venus in front of the Sun. This project is considered to be the first scientific research which used cinematographic techniques.
Ici, au Musée du Cinéma à Paris, est conservé un appareil.
At the Musée du Cinéma, Paris, we have preserved the forerunner of all modern cinematographic cameras. It's the prototype of Janssen's photographic revolver, which was built in 1873 by the clockmaker Eugène Deschamps. At the front is the clockwork mechanism, the aperture for the light to enter, and the shutter. At the back, we can see the plate with its toothed outer ring. This plate moves at intervals by means of a cam, which is seen here.
Janssen and his team went to Japan to try to record the transit of Venus. The plan was to point the mirror of a heliostat at the Sun and project the image into a horizontal telescope. Attached to it was a revolver which could record 48 images in 72 seconds. The technical company Redier built this new model. Janssen made an attempt to use this first scientific cine camera designed for time-lapse recording in Yokohama, Japan, in December 1874. The technical structure of the apparatus was illustrated in the scientific journal La Nature. Here we see it from the front, from the side, and here in an exploded drawing. The upper casing, seen here in orange, contains the clockwork drive which operates the whole mechanism. The shutter disc is shown in blue, and the yellow part is the daguerreotype plate. The letter F shows the position of the aperture, which allows the image from the telescope to enter as soon as it lines up with one of the 12 openings of the rotating shutter. The daguerreotype plate stops whenever an image passes through the fixed aperture and a shutter opening. On this original plate, Janssen recorded a simulation of the astronomical event. On one image from this plate, we can highlight the area of each exposed frame and the curved line representing the edge of the Sun. The small disk is the planet Venus beginning to pass in front of the Sun. Here are the images of the Janssen plate transferred to film. In this animation of the original pictures, the movement is speeded up 30 times above normal. Some months before the actual event, Janssen presented an example of this simulated transit to the Académie des Sciences. There is one plate of the real transit of Venus kept at the Science Museum in London. It was recorded by British astronomers who used a different version of the Janssen apparatus. These markings give the exact time of the recording of about 60 frames. For the first time in the history of science, an automatic instrument had been employed to record a dynamic event in a series of images which could be analysed later. Unlike Janssen, the French physiologist Marais worked on human and animal locomotion. He published his results in the same year that Janssen developed his first apparatus. Before he used photography, Marais invented a graphic recording method which was based on pneumatically transmitted signals. Impulses were emitted from sensors on special shoes as weight was placed on them on the ground. These signals were recorded on a kymograph. The remains of one of the original research shoes used in the experiments are preserved at the Musée Marais in Beaune, France. Marais also applied this method to the study of flying birds. Although his amazing mechanism was complicated, the bird could move freely enough for its movements to be recorded. He also calculated the frequency of the wing stroke in free-flying birds, using both electrical and pneumatic signals. The movements of the legs of horses were another subject for Marais' recording technique. Human perception is not capable of analysing such a rapid succession of movements. This system of investigation allowed very detailed study. Here are other remnants of the experimental equipment used more than 100 years ago. From the pen traces, diagrams were produced where the graphic recording method showed the spatial and temporal relation of the legs of the horse at each type of pace. This sequence from the French film La Naissance du Cinéma, produced by Roger Lénard and the film historian Georges Sadoul in 1946, is a reconstruction of Marais' recording method to analyse the movements of the horse. Every contact with the ground is marked on the rotating kymograph held by the rider. At the time, horse racing was a very popular sport and created considerable public interest. In 1873, Marais completed this graphic recording research on horse locomotion and published the results in his book La Machine Animale. At about the same time, the photographer Muybridge is said to have taken a still photograph in San Francisco, California, of the silhouette of a horse moving at full speed. Unfortunately, the original image was never found. The name of Edward Muybridge, a photographer born in Britain, was spread by advertising which appeared on the west coast of the United States. In 1877, he published an image of a running horse which was still greatly retouched. In the following year, he did manage to print an unretouched series of automatic electrophotographs. They were taken with an exposure of 1/2000th of a second at intervals of 1/25th of a second. The size of each image was about that of a modern 35mm photonegative. This card, designed for sale commercially, shows on its reverse side a detailed written analysis of the stride cycle of a running horse. Muybridge's work, as it became more popular, was parodied in cartoons in Californian magazines. By contrast, Muybridge received recognition from serious publications like The Scientific American. This journal devoted one complete front cover and several articles to his work. The Muybridge photographs were also published in France. In fact, they encouraged the physiologist Marais to use photography in his own studies. In California, a special experimental track was built on a ranch belonging to Leland Stanford at Palo Alto. This magnate, politician and racehorse owner commissioned Muybridge to carry out his experiments. A series of still cameras was aligned along the track. The shooting area was equipped with a white background and reference marks. The cameras each had 2 lenses to make a double exposure. In this reconstruction from La Naissance du Cinéma, we see the new electromechanical shutters working with remote and automatic switches. This extract from a German animated film of the 1930s illustrates the operation of one switching mechanism. The racing papers publicised Muybridge's results, giving the reader the chance to analyse the phases of a stride and the complexity of movement of the 4 legs. Previously, this would not have been possible. This is a picture from a series of 8 phases of a pony while cantering. It shows the young son of Mr. Stanford, photographed by Muybridge to please his sponsor. A horse skeleton was specially prepared and photographed several times to provide a better understanding of its physiology. As well as his work on horses, Muybridge experimented with serial photography of athletes. Some of his picture series were popular with the public and were printed for use in optical toys like the zoetrope, otherwise known as the Wheel of Life. In Europe, Muybridge pictures became well known. The zoetrope, or the phenokistoscope, its forerunner, was offered to the public through the pages of magazines like L'Illustration and La Nature in France. Using his own photographic images, Muybridge copied them in coloured paint onto glass discs. This enabled him to project them in public. In many of these painted images, the natural shape of the figures was modified to compensate for optical distortion introduced by rotation of the disc. Elongation of the body of the lion is particularly marked. He constructed a projector called zoopraxiscope for showing his moving images at public lectures. At the Muybridge Museum in Kingston-upon-Thames, near London, the original zoopraxiscope is on display next to a modern replica. For the purposes of this film, the original zoopraxiscope, which is still in working condition, was run once again using a modern electric light source. On this Muybridge apparatus, replacing a disc is quite simple. In the winter of 1881, Muybridge presented his moving pictures to the physiologist Marais, the painter Meissonier, and other scientists and artists in Paris. The following sequences have been animated from the original Muybridge discs. Having seen the projected images by Muybridge, Marais realised the importance of serial photography for his own research and designed himself an apparatus to shoot movement. The photographic gun, which was invented by Marais in 1882, is shown here being demonstrated by one of his assistants. This engraving was made for publication from this original photograph, which was probably taken by Marais himself at his winter home in Naples, Italy. The French magazine La Nature published the first report on this new photographic device. This is a drawing of the complete gun and its main parts. The cylindrical housing attached to the barrel holds a rotating plate coated with dry emulsion, on which 12 images could be recorded within 1 second. The plate was octagonal, or round, and less than 10 centimetres across. Using this device, it was possible to shoot moving objects. In this way, Marais was able to analyse the wing movements of birds. The photographic gun had a separate drum magazine which held up to 25 spare plates. This is a model of the drum magazine exhibited at the Deutsches Filmmuseum in Frankfurt, Main. The model shows how the glass plates were stored inside. Marais' photographic gun, which was inspired by Janssen's photographic revolver, represented a conceptual and technical advance on Muybridge's technique of serial photography. When the trigger is pulled, a clockwork mechanism moves the plate around, allowing the 12 images to be exposed. Each exposure lasts 1/720th of a second. In front of the house, which was owned by Marais near Beaune, an original photographic gun is demonstrated to show its operation in detail. One plate is inserted from the drum magazine. The shutter spring is cocked. Then the gun is ready to take pictures. When one plate has been exposed, it is replaced in the drum magazine. To reload the gun, a new plate is dropped into place when the magazine mechanism is turned to the next position. Now the gun is ready to shoot again. At the same time, Marais introduced another type of cine camera. A crank was used to turn a shutter which had several openings. Here, the photographic plate remains static. This new apparatus was called le chronophotographe. It was another great advance in the technique of shooting movement from a single camera. It represents the technological link between the early photographic apparatus and the later cinecameras. This example demonstrates the new technique. In front of a dark background, a moving model in white could be recorded as successive images on the same plate because the photographic emulsion had low sensitivity and allowed multiple exposure. However, if the rate of shooting was increased, the images overlapped. Despite this, these old plates can be successfully animated today. This reconstruction, taken from La Naissance du Cinéma, shows how Marais modified his method of recording. He used a model dressed completely in black. The parts of the body which were to be recorded in motion carried thin white lines and dots. Fast movement appeared on the plate as a white trail, while slow-moving parts were more clearly defined. Here's the recording of a jump. From schematic representations based on these plates, Marais gained valuable analytical information. Sometimes these images had an aesthetic value too. By superimposing successive images, we can recreate the original motion. By combining the technique of the photographic gun with the chronophotograph, Marais then designed an apparatus with a rotating plate. He is probably the subject shown on this plate, which was taken during a test with a new camera. This model, on show at the National Museum of Technology in Prague, is of the Marais Experimental Station, which was founded by the Collège de France in 1882. Here is the original Station Physiologique, which no longer exists. Later on, a tower was built to provide an aerial camera position. In this early engraving, we see a chronophotograph mounted on a railway wagon. This way, it was easy to move the camera to obtain the correct field of view. The frame rate was controlled by a system of weights acting on the rotating shutter disc. Experiments were also carried out at Marais' villa in Naples. This chronometer, exhibited at the Cinémathèque Française, was used to measure the speed of motion and check the frame rate. The position of the arrow in relation to the marks indicated exposure intervals. In spring 1884, Marais published the results of his physiological studies on motion employing chronophotographic techniques. The French Ministry of War commissioned Marais to analyse the posture and movement of soldiers. Marais examined the trajectory and acceleration of physical objects, the vibration of a rod, the rotation of a stick or of two connected spheres in the air, and the trail of a bouncing ball. With this apparatus, he recorded the flight of a dragonfly which had been fixed to the pivot. Gold powder on the insect's wings traced their movement in flight. Marais was also involved in the early development of flying machines. With his chronophotographic material, he obtained a great deal of data for detailed analysis. The images for studying the flight of a gull were shot at 50 frames per second. To produce completely separate images at this same speed, Murray invented a system for taking alternate shots on two different parts of a plate. When these images were put on the disc of a phenakistoscope, one cycle of the wing beat could be observed 5 times slower than the real speed. To get a deeper understanding of the physiology of birds in flight, Murray planned a complex system of synchronous shooting from 3 points of view at right angles to one another. He could only partly accomplish his idea, but in the process he obtained important reference in 3 dimensions. Some of these images are particularly beautiful. Better pictures of a bird flying towards the camera without lateral displacement were taken using a special apparatus. The red object indicates the position of the plate. The dark line, the rotating shutter. And the blue object is a moving mirror. Using this device, Murray obtained a series of laterally displaced images of a bird flying towards the camera. A similar technique is still employed today in modern high-speed cine cameras, over a century after Murray's first experiments. The remnants of the original apparatus which controlled the position of the moving mirror can be seen at the Musée Murray in Beaune. Visual material shot on the chronophotograph enabled Murray to commission a very interesting piece of work. A sculptor from Naples created in brass a model of the intertwining figures of a flying bird with proper spatial displacement. This sculpture, though it was made for a scientific purpose, anticipates the style of similar works of art like those of the Futurist movement. Taking every alternate position of the intertwining birds, Murray separated the 3-dimensional figures to show the successive phases of a full wing beat. A copy of this sculpture was assembled in a large zoetrope. Nowadays, many of these zoetropes are on display in museums all over the world. Looking through the slits of this apparatus, we can see the bird apparently flying in slow motion. By changing our viewing position, we can see the birds flying towards us. Or flying away. This animation is based on Murray's model. For his chronophotographic researches, Murray is considered to be a pioneer of aviation. In the mid-1880s, The work of Edward Muybridge was sponsored by the University of Pennsylvania at Philadelphia. He shot about 20,000 serial photographs in the study of biolocomotion. Compared with Maret's single-lens camera, Muybridge was still using a camera with 12 lenses plus one lens for focusing. On the back, we can see the series of electrically driven shutters. Combined with a clockwork mechanism, these shutters allowed him to take photos in rapid succession. A single plate holder had 12 square spaces. Muybridge was permitted to have his open-air studio in the courtyard of the veterinary faculty. Here, his crew is seen among the equipment. This original sketch shows how the equipment was arranged. Here we see the 3 different camera angles. This animation shows the technique of synchronous shooting. The model is shown from the perspective of the middle camera position. In this catalogue, Muybridge recorded the 781 plates published in 1887. The pages of the catalogue list in columns the data for each plate. The identifying number of the model, an indication of sex and costume. Then they show the number of frames for the phases of movement, divided according to the points of view into lateral and front or rear foreshortenings. In the third group of data, we see the time interval between each shot in thousandths of a second. Altogether, 95 plates were devoted to horses, and 123 to other animals. Some were photographed at the zoo. Muybridge occasionally succeeded in shooting birds in flight. This series of drawings illustrates the scientific use of his plates for the study of animal gaits. These animations were produced by reshooting each image of a plate onto one frame of film. A full cycle of motion was repeated several times. Here, to improve quality, the background has been replaced. More than 2/3 of the plates record human subjects. Occasionally, Muybridge appears as a model himself. Besides people recorded at work, some series show hands in motion. They anticipate the technique of the close-up. These animations have been taken from the front and from the lateral views. These hands beating time were shot at an interval of less than 1/5 of a second. When images of the first and third rows are shown in succession, a circling effect is obtained. This peculiarity has been observed on the plate where a woman appears to be spanking a child. model number 42 performing a head spring. From the second camera angle, a pigeon comes into shot. The time interval between each frame is about 1/10 of a second. The medical faculty asked Muybridge to document some cases of abnormal movement. This case of obesity was not included with the pathological cases. Muybridge titled it "Arising from the Ground." Gymnastic movement was one of his principal subjects. This model had a rod attached to her hips to help measure their oscillations. Even though he was commissioned for scientific purposes, part of his work is ambiguous. Some of his images seem to have commercial appeal. Artists would use them instead of live models. Many plates from the published collection Animal Locomotion show models performing simple actions, like this person acting shame. In such cases, Muybridge anticipated the function of a fiction film director. Selected Muybridge plates were bought by universities, noted artists and scientists all over the world. Muybridge spent his last years lecturing on his work with animated projections. In 1888, Marais managed to record images on a short roll of the newly available photographic paper. His first version of a cine camera could only be operated from inside a darkroom, while the next model was portable. This small box held the mechanism for keeping the film running.
Le musée de Beaune possède cet appareil centenaire, construit en 1888.
This 100-year-old apparatus at the Musée de Beaune is the connecting link between the chronophotograph with fixed plate and the modern cinecamera. Here, a reel of sensitized paper is placed, which is then passed in front of an aperture and onto a take-up reel.
Lequel film défilait devant la fenêtre et se réenroulait sur une bobine réceptrice.
These drawings are based on one of the first paper roll films. They were published in the scientific magazine Archives de Physiologie in July 1889. Marais's cinecamera assumed its definitive form shortly afterwards. This chronophotograph, which already used celluloid film, records images on separate frames without overlapping them as before. This animation shows how it works. Some original models, displayed at various museums, are still in working order. This engraving of a cameraman shooting with a chronophotograph in front of an aquarium was published by La Nature in 1890, 5 years before the first projection of films for entertainment. At Naples Aquarium, Marais studied marine animals and analysed their motion from various angles. Today, it's possible to animate his shots. These photos were taken on vertical frames in 1891. They're referred to as the wave by some film historians. This piece is probably one of the first films shot at the Station Physiologique in Paris. In the following years, Marais and his assistant Demeny continued to study human motion. Most of these animated sequences were made by reshooting each original frame twice. At the same time, he resumed work in his principal field of research, animal motion. Understandably, he often came back to his favourite subject, the horse. From his recordings, Marais obtained a wealth of scientific information, also depicted in diagrams. Chronophotography enabled Marais to make horizontal close-ups of horses' legs. To make full use of the roll film, which was only available in very short lengths at that time, the camera could be turned on its side and the height of the frame could be changed. A photograph from the archives of the Collège de France seems to suggest that Marais also tried to film the same subject with 2 cameras simultaneously. To study locomotion on this novel vehicle, he applied both the old system of chronophotography with still plate and the new one with moving film. In 1892, Marais tried to build a projector for screening repeating cycles of motion. However, the results were not satisfactory because his film lacked perforations. On the other hand, he achieved good results by combining his camera with a microscope. Here are a few examples of his microchronophotography. Marais also produced stereoscopic images of geometric solid bodies by rotating flat, 2-dimensional objects. Towards the end of the century, he experimented with fluid dynamics. For this work, He is considered a pioneer in the technique of filet de fumée, still used in the study of aerodynamics today. In another experiment, he attached his chronophotograph to a wave tank to study the behavior of liquids. Sunlight was used to illuminate particles suspended in the fluid. To pay tribute to Maret's work, an institute was founded and located at the Station Physiologique, initiated by an international congress of physiology. Here, Lucien Bulle, who'd been an assistant of Maret in his youth, is seen demonstrating the operation of a chronophotograph in the laboratories of the Institute. This sequence was taken from the film La Naissance du Cinéma. In his last cine-camera design, Maret returned to the idea of the photographic gun. He developed two prototypes which used 35mm film without perforations.
Ce fusil photoélectrique conservé à la Cinémathèque française.
The photoelectric gun, which is kept at the Cinémathèque Française, was built by Maret in 1899. The butt contains an electric motor connected to a battery.
Ici la détente.
Here is the trigger which starts the film. There are two reels which hold up to 30 meters of film. Here is the pressure plate for intermittent motion control.
Qui interrompait ou relâchait le mouvement du film au moment de la prise de vue. Ici simplement un obturateur rotatif.
Here there's a rotating shutter and at the end the lens. The driving mechanism is attached all along the gun.
D'un bout à l'autre du fusil.
From the supply reel, the film is transported by a pinch roller towards an intermittent pressure plate, and then passes in front of the rotating shutter. Finally, the film is wound onto the take-up reel. This handheld apparatus anticipated the lightweight portable cinecameras of future years.
Nous allons voir maintenant un petit film original de Maret.
This is a piece of original Maret film, a chronophotographic strip 9 centimeters wide and without perforations. We found hundreds of these in the Cinémathèque Française, and before they could deteriorate further, we've copied them onto modern film stock to preserve the images.
Pour en garder l'image.
Special mention must be made of Maret's studies of falling animals. The most impressive example is the cat turning from its back to its feet while falling. Some sequences were taken at 60 frames per second. As early as 1894, these images were shown on a zoetrope to the Académie des Sciences, causing a great deal of discussion. Today, we can see Maret's images animated.
This 9-lens camera was built in 1883 by the Frenchman Albert Londe. Its design combined the techniques of Marais and Muybridge. It could record either a single frame or up to 9 frames in rapid succession. The shutter was driven by an electric motor. This is one of the few surviving plates. This engraving shows a battery connected to the camera and a metronome working as a timing device for intervals and exposures. Londe was head of the photographic service at the Salpêtrière Hospital in Paris. This 12-lens camera he had built in 1892 recorded images on a single square plate. Each lens had its own shutter. With this timer, seen here with its switching equipment, it was possible to take up to 12 exposures in 1/10 of a second. In the open-air studio of the hospital, Londe carried out his photographic experiments, now and then visited by Marais. These serial images were recorded for frame-by-frame analysis. In the course of research with Professor Charcot, Londe shot examples of human pathological movement caused by nervous diseases. These plates illustrating medical cases were only recently discovered and are reproduced here for the first time. While animating these plates for this film, the effects of vertical and horizontal parallax had to be reduced. Despite his extensive work for science, Londe is now best known for his few non-scientific recordings. This camera, which is similar to Londe's first design, was built in 1889 by Hippolyte Seybert. Recording 6 images at a very high speed, it was used for analysis in the field of ballistics. These animated sequences show torpedoes being launched at a speed of 20 meters per second. The German photographer Ottomar Anschütz first gained public recognition through the excellent quality of his snapshots of popular subjects. In 1887, he started publishing printed copies of serial photography, for example, of an athlete throwing a javelin. The movement shown in these 11 frames lasted just over a second. In this animated sequence, each original still frame was shot twice. This is the only known illustration of the apparatus used for serial shooting by Anschütz. It appears to resemble the Muybridge camera setup. Anschütz converted the zoetrope into the Schnellseher, an ingenious device for viewing series of images arranged either horizontally or vertically on strips of paper. Here, a cycle of these images has been animated. The moving pictures were viewed through slits in the rotating drum. Variation in speed allowed the viewer to get a clear impression of movement. By changing one's viewing position up and down the rows of slits of this tachyscope, it is possible to see the horse moving forwards, backwards, or running on the spot. This portable tachyscope, designed for entertainment, became popular with the public in various countries. In contrast to this, the photographic work of Anschutz also included studies for military training. These were financed by the Prussian government. In America, the new projecting tachyscope, the elektrischer Schnellseher, was well received. The images were projected using a flashing light. As early as 1892, thousands of people came to watch these projections. An improved model, coin-operated and designed to be used for individual viewing, attracted great public attention. Here, some of the original tachyscope images have been animated. A recording technique which avoided the parallax effect was used by the gymnastics teacher Dr. Ernst Kohlrausch in Germany. These images, animated for this film, were shot in the early 1890s. This is a double exposure which may have been used for the training of gymnasts. The wooden cover of this original camera has been removed to show the lens system. Here we can see 3 of 24 lenses arranged equidistantly around the wheel. These lenses moved in front of a single fixed aperture to make an exposure as the wheel turned. Here is a view of the rear side of the apparatus. The Deutsches Filmmuseum in Frankfurt on Main has preserved this original camera. In this shot, we can see the individual plate holders. Kohlrausch built a second camera which had a lens system separate from the plate holder wheel. A small wheel with 4 lenses and a large wheel with 25 plates rotated synchronously. This technique also allowed Kohlrausch to shoot from a single point of view without the parallax effect. This fragment from his recordings of 1896 shows an example of pathological movement. Georges Demeny was technical assistant to Professor Marais in Paris since 1881. He took great interest in the study of new methods in gymnastics. When Marais was working in Naples, he regularly corresponded with Demeny in Paris to discuss the technical aspects of their experimental work. With this phonoscope, first demonstrated in 1891, Demeny tried to help deaf mutes to decipher words from mouth movements. This is Demeny himself mouthing, "Je vous aime." Madame, bonjour, madame, is spoken by this young man. The images were shot using a Marais chronophotograph. For projection purposes, one series was compiled on a disc. Here is a replica of the phonoscope exhibited in the National Museum of Technology in Prague. Demeny also had the idea to use his phonoscope commercially for viewing so-called living portraits. In spite of the popular appeal of these portraits, Demeny's venture was not successful financially. His company never paid dividends to its shareholders. It was the Gaumont company which exploited the new camera Demeny had designed using an eccentric cam. This cam device controlled the intermittent movement of the film. The camera was widely used in the early days of the film industry. In 1900, Gaumont produced Demeny's pocket camera called the Chrono de Poche. It was driven by a crank or a clockwork spring and could be used for shooting, printing and projecting. Images were recorded on 15mm film with a central perforation. After Demeny, Lucien Bull became Marais' assistant and also his model. At first, Bull specialized in research in cinematography. This apparatus for time-lapse recording combined a timer A, a chronophotograph B, and a microscope C. Here is an example of cinematography shot on Bull's equipment. In 1902, Bull devoted himself to high-speed cinematography using a stereoscopic camera. The lighting system for this camera used an electrical contact device which caused a spark flash synchronized to each frame of exposure. The two strips of film, which had no perforations, were fixed to the outside of a rotating drum. Insect flight was one of his main fields of study. In 1904, he demonstrated to Marais film strips recorded at 500 frames per second. The metal pointers in the lower left of the frame are a timescale device. The maximum speed of filming was 2,000 frames per second. These are soap bubbles shot through by small projectiles. This plate by the Austrian Robert von Lentenfeld, which is animated here, was recorded in 1903. Using the moving mirror technique inspired by Marais, von Lentenfeld achieved a recording speed of 2,000 images per second. Around 1910, this stereoscopic high-speed camera was built by the Frenchman Pierre Noguès at the Institut Marais in Paris. Following in Marais' steps, Noguès studied the flight of birds, using a frame rate of 240 pictures per second. In real time, one cycle of these animated images corresponds to 1/10 of a second. Continuous movement has been obtained here by repeating the cycle. This is another example of Noguez's high-speed work. In 1912, using the prototype of this camera called the Ultra Cinema, he recorded 300 pictures per second on 35mm film, employing an intermittent mechanism. This is still the maximum frame rate obtainable with this technique even today. The fine quality of this original Ultra Cinema film by Noguez set a standard for the development of high-speed cinematography.
Time-lapse cinematography allowed botanists to record and analyze plant growth movements for the first time. Only with the help of time-lapse recording can the human eye perceive these slow movements and their varying rates by day and by night. 1 second of screen time here corresponds to about 2 hours in real time. The shooting of this sequence took 11 days. It enabled a precise chronology of root and sprout development. This experiment recorded on film over a period of 35 hours, shows the phenomenon of geotropism. When placed in a horizontal position, the tip of a plant bends away from the pull of gravity to reassume a vertical position. This sequence was animated from selected frames which were published in a scientific journal. The original film has been lost. These cinemicro shots, taken at a rate of 1 frame every 8 seconds, were originally recorded at the Institut Marais in Paris. Microbial flora, bacteria and infusoria were featured in this piece of cinemicrography which used the dark field technique. This film, which is part of an educational film series, has a total running time of 4 minutes. The spirochete, which causes syphilis, was discovered in 1905 and was shown for the first time in this film. Commandant submitted this material to the Académie des Sciences in Paris as part of his doctoral thesis. This plate has been taken from a publication which reported on how locomotion was affected by surgery on the cerebellum. The original film was shot by the Italian film pioneer Filoteo Alberini. Here, the published pictures have been animated. Starting as early as 1898, these pathological movements were filmed at the hospital Pantelimon in Bucharest. Here we can see the original negatives. These films had only 1 pair of perforations per frame, typical of the system used by the first Lumière cameras. These extraordinary films, which are an important record in the history of medicine, were considered lost forever until their rediscovery in 1970. These films provided an opportunity to analyze increasing movement disorders produced by progressive ataxia. The film recording made it possible to study in detail the disruption of movement from organic hemiplegia. This woman's case of hysteric hemiplegia, said to have been caused by a quarrel with her husband, was treated and cured by hypnosis. The filming of this operation took place in the courtyard of the hospital to obtain better lighting. Posadas invented a rapid technique for this kind of lung operation to increase the patient's chances of survival. Travelling to various countries around the world, he used this film during lectures to describe his operation. The original print, which runs for 3 minutes, was rediscovered in 1971. The surgical technique used to separate these Siamese twins was filmed by Clément Maurice, who had been technical assistant at the Lumière Company. This film seems to be the only remaining record of the extensive work of Doyen. In fact, in 1898, he was the first to use film recordings, not only for teaching, but also to improve his own surgical technique. Among his French colleagues, this film caused great controversy. The presentation of these early filmed operations may cause surprise and amusement, but these documents have their value as records of the history of surgery. This sequence, shot by Roberto Ormeña, shows a case of induced hysteria. The patient is wearing a mask to remain anonymous. The original film consisted of several sequences. Its first screening took place at the Reale Accademia di Medicina in Turin. Negro made this film to give all students an opportunity to learn from the observation of unusual cases. This is a frog's leg moving. A human heart beating. And this is stomach movement following a bismuth meal. These first X-ray films were shown to the Philosophical Society in Glasgow and also to the Royal Society in London. These images were directly recorded from X-ray equipment on double emulsion film negative 60 mm wide and specially produced by the firm Lumière. The actual digestive movements last for 5 seconds. These attempts to film X-ray images from a fluorescent screen were made at 2 frames per second. This is probably Commandant's own hand shown here. At the Military Academy of Berlin, these shots were taken at a speed of over 5,000 frames per second. One of the purposes of this work was to study the impact of bullets on human bones. Using drawings on paper, not on celluloid, Munch made 50 films on mathematical subjects. 20,000 of these drawings are preserved in the Deutsches Filmmuseum in Frankfurt on Main. Munch, who was a secondary school teacher, was probably the first to illustrate the laws of geometry through film and to use the medium for teaching. Flip books were also produced from his drawings for use as learning aids. These film strips are 9 centimetres wide and have no perforations. They were shot at the Station Physiologique with a Marais chronophotograph by Charles Comte. The recordings show the first application of cinematographic techniques in the study of anthropology. Regnault took these shots to compare different ethnic groups in movement. Some sequences were filmed at the Exposition Ethnographique in Paris. These are among the earliest recordings used in field research. They were produced with a Lumiere camera on the Torres Straits area between the northeastern coast of Australia and Papua New Guinea. Here is an attempt to make a fire. Following the example of the Cambridge expedition, Spencer filmed the Aboriginal tribes of Central Australia. This is one of the Chichingallah ceremonies. This dance, with symbolic masks of hornbill and snakes fighting, was filmed by a German expedition to the islands of Melanesia and Micronesia. They also filmed the activities of youths in this community, riding waves on wooden boards. This film record shows that the sport of surfing was known in other areas of the Pacific, apart from the islands of Hawaii, before it became a modern fashion. Mr. Schilling, the photographer and cameraman on this German expedition, also made many detailed recordings of craft works. These early recordings represent the start of modern visual anthropology. They were made for research purposes, but are now of value as a record of disappearing cultures. This sequence shows an early example of pictures and sound recorded simultaneously. This modern synchronized version was assembled in Vienna in 1987, when the original Edison wax cylinder was found.